All right, so scientific notation is a topic that's covered not so much in algebra, but it will definitely appear on the 8th grade SBAC. And since it has to do with exponents, let's put it in right here. Scientific notation is probably something that you have seen when you multiply numbers in a calculator that are too big for the screen to hold. So it'll give you a number, point something, and then it'll say to the exponent. Well, this is always going to be with a base 10. So we have blank point, blankety blank, times 10 to the some power. So what we're going to do is two things very quickly. We're going to go from scientific notation into the standard form of a number, which it's not like graphing standard form. It just means a regular old number. And then we're going to go backwards and go from standard form into scientific notation. So these are just regular old numbers, although very, very small and very, very large. And we're going to put them into scientific notation. So what I think makes sense to do first is convert from scientific notation. So here we have times 10 to the 9th power. So you know it's in scientific because there is one decimal that appears or one number that appears before the decimal. Now, it's a very, very common mistake for people to just add 9 zeros right here. So they go 3.12 and then they add 9 zeros. It's not what we're going to do at all. Here's the trick. We're going to scoot the decimal, and that's it. And we are going to scoot the decimal 9 spots from where it currently sits. So if I just write this 312 as it is, but I skipped the decimal here, I need the decimal to move 9 total places, and since it's positive 9, we're going to go 9 to the right. So from here, this was over 1 over 2. So to get to 9, I need 7 more. So I'm just going to throw 7 zeros on here. And that is where the new decimal lives. Now, of course, after a really large number like this, you don't need a decimal point, but I'm putting it there for emphasis right now. To write this properly, let's throw some commas in here every 3. So now you're able to see what number that is. Next example, we have a 6.84. So again, I'm going to copy the 684. My 3 that is positive says scoot the decimal 3 places in the positive direction. So go right. So that means from here we go 1, 2, and 3, which means the decimal is going to end right there, and we need to add just 1 0. So this number is 6,840. Here's something new. It's a negative. So you guessed it. We're going to scoot 4 places, but this time in the negative direction. So number line left. So from here we go 1, 2, 3, and 4. So this is the new decimal. So this is already taken, but we have room here for 1, 2, 3 zeros. So 0.000. 135, and it's a very, very good habit to get into. Never start with a decimal point. It always gets a 0 in front of it. And of course, this 0 doesn't count as movement. That's just to say that this number is below 1. So 4 places to the left. This happens from time to time, and I feel like the only reason you would see this is like a drag and drop question or a multiple choice question where they say select all that are equivalent to this number. Take a look at this one. It's not actually in scientific notation, and I'll tell you why. It's because number, this is 14. So really, if you think about it, the decimal is there. Now, if I asked you to put this into scientific notation, it would require that you move the decimal, and it's 1.4. It's not proper scientific notation right now. Anyway, we're not there yet. We're just moving 5 spots to the right. So in this situation, 5 spots to the right is actually the equivalent of 5 zeros, which means this number is 1,400,000. And then last practice example that says go 3 left. 1, 2, and 3. So that left us a spot for 1 0, and then our 3, 8, 6. And then remember, don't just leave that as the opener. Put a 0 in front of it. So That's from scientific notation into a regular old normal person number that you can interpret, standard form. Okay, scooting over, we go from standard into scientific. So if you look at the pattern here, you'll notice all the positive exponents are really large numbers because we scoot to the right where we have larger numbers. The negative exponents produced smaller numbers, right? Decimals, not giant numbers. So if you take a look at this, it's probably going to have a negative exponent because now when we're moving into scientific, we need, first of all, gather all the numbers that aren't zero. So I'm going to select this chunk, 4089. And some people will argue, oh, but there's a zero in there. Well, that zero has to be there. Just take out all the zeros that are all in a row. Now we're going to write this in sort of this format. So we need number, point, number, number. So the decimal goes after the first digit. So in here, it's going to be 4.089. Now, up top, it always says that it's going to be times 10. And then since this is a small decimal, our exponent will be negative. The only thing now that you have to do is count. So where was the decimal and where did we replace it? So this is going to go 1, 2, 3, and 4 spots over to reach the spot where we decided it had to be. Same thing here. This is going to be all the numbers that are not zero. So don't stop at 389. We need all the non-zero numbers in a chunk. So this is kind of long. We're going to do the whole thing. It's 3.89051. Of course, the decimal goes after the very, very first digit. Scientific notation is always times 10. This is a really large number, and really large numbers are going to have positive exponents. So where was it when we started? Well, it was invisible back here. And then where did we put it is clear over here. So we need to count the number of spaces we moved, and that will be our exponent. So with the commas, it makes it a little easier. This is 3, 6, 9. That's 12. And then we have even one more to get between there. Is going to be 10 to the 13th power. Now you can always check your work. If you're not sure about the exponent 13, try it this way, right? This says, hey, move 13 to the right. So you can scoot it, scoot it, scoot it, and see if it ends in the appropriate place. Two quick applications of this. Sometimes you'll be asked to put these in order from least to greatest. The 5.2, the 1.9, and the 3.8 really don't matter. We're just looking at the exponents. What is the smallest number here? Well, -4 says you're going to scoot 4 places to the left. So this is going to be 0.000 something. That's tiny, especially when these are 2 and 7. So you really shouldn't have to show any work. It's just think about the exponents. -4 is going to cause a decimal way below 1. Now this to the second, that's the number 380. Well, yeah, 3.8 is bigger than 1.9, but again, over twice is 380. Over 7, this is a 19,000 something, larger than that, I don't know, 1,900,000, but 2 places is going to be a much smaller number than 7 places. So least to greatest, this would be smallest, then next, and then last. And we'll finish up with this. These come from chapter 6, 6.1, Rules of Exponents. It's familiar. So the thing here is, I encouraged you to separate your division problems and treat them like 2 separate problems. So here I have a 2.8 divided by 4. You can probably do this without a calculator because if you squint and you pretend that decimal's gone for a second, see how it says 28 over 4? That's just 7, but I'm going to call it 0.7 here. So if that's 0.7, then there's times. Oh, wait a minute. Where do all the 10s go, top or bottom? All the 10s go to the top. The reason 10 goes on the top is because 3 is more than -2. 3 is more than -2 by how many? Remember, it's not 1. It's not 3 minus 2. It's 3 minus -2. So you could say that this is 0.7 times 10 to the 5th. But I ought to tell you, this is not proper scientific notation because you're supposed to have a non-zero digit and then the decimal. So here's what I'm going to do, and you'll see the pattern. If I start with this 0.7 and see how it says move it 5 times to the right, I'm going to go 1, 2, 3, 4, 5. That means this is 0, 0, 0, 0. The standard form equivalent of this problem is 70,000. Now, take 70,000 and write it in scientific notation. Well, okay, that's 7.0 times 10 to the how many? So right here, 1, 2, 3, 4. So this is one way to do it. I just don't want you to fall for the idea that this is in scientific notation because it's not. So I'll teach you something real quick. See how 0.7 was a small number, and when it became 7, it got larger because 7 is more. So I moved 1 decimal place and I got larger, which means your exponent has to make up for that, and it's going to move 1 also from 5 to 4, but the opposite direction, smaller. So this one went smaller to larger by 1 position. So this goes largest to smaller by exactly 1 position. Now this second one, we're not going to run into that. Again, squint your eyes. 33 divided by 3 is 11, but with a decimal. Times 10, all the 10s go on top. The reason is because 4 is more than -6. Not 4 minus 6, but 4 minus -6. This is 1.1 times 10 to the 10th, and it is in proper scientific notation because the decimal is after the first non-zero digit. So there you go. You'll definitely see it. We won't use it much in here, but at least you have it. See you soon.